Our final topic for this week is unrestricted grammars and their relation with Turing machines. Okay, so once again this is a recapitulation of the Chomsky Hierarchy. So let us start with this. So we know that grammars have some correspondence with types of languages and types of languages with types of automata, and these rules pertain to this kind of grammar. So let us see what Chomsky mentioned. So first, type 3 grammars, they are also called linear or right linear grammars. They are equivalent in expressive power with regular languages, which in turn are equivalent to finite automata. So whether deterministic, non-deterministic, you add epsilon transitions, they are the same. Or you can also talk about patterns like regular expressions. They are all equivalent. And in a type 3 grammar, every rule or production is of the form: a terminal can generate some non-terminal symbol followed by another terminal symbol, or a non-terminal symbol can simply vanish by becoming epsilon. In the next level, we have type 2 or context-free grammars, and they are equivalent to context-free languages. In turn, context-free languages are the languages of all PDA, push-down automata, the non-deterministic version. And here the rules are of the form: a non-terminal can be an arbitrary string of terminal and non-terminal symbols alpha. In the next level, which we have not studied very carefully or in detail, we have type 1 grammars or context-sensitive grammars. So they are associated with context-sensitive languages, which are the languages of linear bounded automata. Here, each rule is of the form alpha A gamma, where A is a non-terminal symbol and alpha and gamma are arbitrary strings over terminals and non-terminals. A becomes beta. This is called context-sensitive because A can become beta only in the context of alpha and gamma. Whereas this is called context-free, does not require any context for converting to alpha. A can in any context become alpha. Here, of course, A can become beta in the context of alpha preceding it and gamma following it. Finally, we have type 0 or unrestricted grammars. They are equivalent to recursively enumerable languages, which in turn are equivalent to Turing machines. I will prove the equivalence of this and this, or this, and here actually anything can be anything. Only restriction that I make is that this part, the left side of a production, must contain at least one non-terminal symbol, which I say as A. So this is the hierarchy of grammars and also hierarchy of languages, hierarchy of automata. So we have studied earlier these things in detail. Little bit of these we have talked about. Now we will look at unrestricted grammars. So first let me define unrestricted grammars formally. Like context-free grammars, it's a 4 tuple sigma n s p, where these individual things are as follows. Sigma is the set of all terminal symbols. N is the set of all non-terminal symbols, and of course we assume there is no symbol common to sigma and n. So n intersection sigma is empty. S is a distinguished member of N, a non-terminal symbol called the stirred symbol. And finally, a set of rules or productions P. Of course, it cannot consist of an infinite set of rules, only a finite collection of rules, also called productions. Okay. This is exactly the same as a context-free grammar. The only difference is that how the rules in P look like. Now, in a context-free grammar, in an unrestricted grammar or type 0 grammar, any production is of the form alpha can be beta, where alpha and beta are arbitrary strings over non-terminals and terminal symbols, with the only requirement that on the left side, that is alpha, there must be at least one non-terminal symbol. And as in the earlier slide, I can write it this way. In order to highlight that alpha contains one non-terminal symbol, so if I call it A, we can also write it as A preceded by anything, followed by anything. This gamma and delta may contain other terminal and non-terminal symbols. Eventually it becomes beta. Beta is also another string of terminal and non-terminal symbols. Okay. And like context-free grammars, I can define the language of G as the set of all W in sigma star, that is set of all strings over terminal symbols only, such that you start from S, make a derivation using these rules any number of times, eventually arrive at W under the rules of G. So that is the language of G. Okay, so let us start with an interesting example. In fact, I will tell you a couple of examples. First one is A power 2 power n. We know that this language is neither regular nor context free. It is context sensitive actually, but I will design an unrestricted grammar instead of a context sensitive grammar. Okay. So now the start symbol is again S, and I will as usual use capital letters for non-terminal symbols, and of course in this case the only terminal symbol is A. So the start symbol is S. Okay. So initially what it does, it generates a single A corresponding to n equal to 0. 2 power 0 is 1, so A power 2 power 0 is just 1A. S has a duty of generating the first A corresponding to n equal to 0. Okay. It will also generate two other things. U. We will see that U will act like a doubler. And here is another non-terminal symbol T, and we will see that this T will act like a terminator. This is a doubler, this is a terminator. Okay. Now let us see how this doubler does. It can vanish, or it generates a capital A and remains. Okay. Well, so for that matter, U is not exactly a doubler, it's actually a doubler generator. It generates this A, this capital A is the doubler. So one by one, U becomes AU, U. It generates some number of capital A's and eventually vanishes. Okay. This is actually context free. So far we have seen context free things. These are all look like context free things, right? These are all context free rules. Now let us see a non-context free rule. It is something like that. So this first A is generated here immediately after the terminator, and then multiple A, capital A's will come here, A, capital A, capital A, capital A, capital A, and so on. Now the idea is that this capital A is a non-terminal symbol. It cannot exist in any final central shell form, which must be over the set of terminal. It's a string over terminal symbols only. So now this rule says that A can move past a small a. Capital A can move past a small a, but the moment it does so, it increases the count of small a's by 1. So 1a becomes 2. 1 small a becomes 2 small a's at the cost of a moving forward this or moving past this small a. So this way, these a's will eventually come left and touch the terminator. So whenever a touches the terminator, a vanishes. It becomes terminator only remains. And eventually, when one by one all a's come in contact with the terminator itself vanishes. Okay. So it is important to note that if the terminator vanishes before converting or before killing all the a's, some a's will remain. And we cannot generate a string over terminal symbols alone. Okay. Now let us see a sample derivation. A power 8, a power 2 power 3 using these productions. So this U will generate 3 capital A's. So this is actually easy. First one is TAU, then U becomes capital A, capital U, again another capital A, capital U, again another capital A, capital U, and eventually U vanishes. Now I have 3 A's. They will try to meet the terminator and eventually get vanished. Okay. So when this A, now there is only a 1 A. When this A crosses this, it generates a couple of A's. Something like this. 1 A now becomes 2 A's according to this rule. Now T has come in contact with the terminator. It vanishes. Now the journey for the next A starts. Capital A, uppercase A. It will, starting from 1 A, I now have 2 A's. Now this second A will move past both the A's, and this A will become 2 A's, this A will become 2 A's. So in total, when this A meets the terminator, there will be 4 A's. So let us see how it happens. 1 A is crossed, so second A is crossed, and terminator has contact with another A, so that capital A vanishes. Finally, starting from 1 to 2, I have 4. This A will again make a leftward journey, meet the terminator, and it will double the number of A's. So this is something like this. 1 A gives 2 A's, next one gives another 2 A's, this. Eventually it vanishes. Now the duty of the terminator is over. The rest, whatever is remaining, no capital A's are remaining, no other non-terminal symbol is remaining. So now, peacefully, the terminator can vanish. 8 A's. Okay. Now let us look at a second example, which is again not context free. A power n, B power n, C power n. I write a type 0 grammar or unrestricted grammar for this language, which is not context free. So here, of course, sigma is A, B, C, the set of terminal symbols. S is the start symbol, and I will use capital letters, uppercase letters for the non-terminal symbols that I use. Okay. So initially, start symbol can be U, T. Okay. Let us see what T will be like terminator, and let us see the role of A, other things. U. T will be the terminator. I will come to the role of T little later. U will generate A, U, B, C. This is a context free fashion. A, U, B, C. A, U, B, C. Once again A, U, B, C. So when U eventually vanishes, what will happen? The string will be of the form A power n bc whole power n. So it's not exactly of this form. A power n is there, and then it's not b power n, c power n, it's b capital C whole power n. Okay. Eventually will vanish. Yeah. Now what we do is that the b followed by c is fine, but a b and then a c is fine, but a c and then a b is not good. Right. So we'll allow b and c to swap their positions. CB can be BC. Good. And then so we'll allow these B's and capital C's generated out of order, not exactly like this, but in the same number. If n A's are generated, n small b's are generated, n capital C's are generated. Only thing B's and these capital C's are not in order. So we allow them to line up like this. Okay. And then what this T will do, it will make a left journey through C and convert each capital C to a small c. And it will eventually vanish. Note that this capital T cannot move past A or B. Okay. In order that the final sentential form does not contain any non-terminal symbol, T must be allowed to cross every C, capital C. And this can happen only when these B's and C's generated out of order are perfectly lined up. Right? So let us see an example. A cube, B cube, C cube. S, U, T. So this is 3. So you will generate A, U, B, C, another A, U, B, C, B, C, A, U, B, C, B, C, B, C. Eventually T will vanish. Now one by one I need this out of place C's to line up perfectly. So maybe I made a mistake. No. Okay, fine. Fine. So this CB becomes BC. Okay. So this C goes to the correct position, B comes before. Okay. This C and B is once again in a misplaced position. So I'll once again apply this rule and like this. So this C moves past, but once again this B is in conflict with the order. So another application of that rule. Now all the B's and these capital C's are lined up. Now this T will move from here. It will convert all these capital C's to small c's and then eventually vanish. Okay, good. Now, what is the relation between unrestricted grammars and Turing machines? So this theoretical thing we have to look at. First theorem, given any unrestricted grammar G, there exists a Turing machine M such that the language of that machine is same as the language generated by the grammar. And conversely, we will show that if you are given a Turing machine M, we can develop an unrestricted grammar that mimics the working of the Turing machine and accepts and generates exactly the same set of strings as the Turing machine accepts. Good. So the first theorem is a little bit easier to prove. Let us do that first. Given an unrestricted grammar, I want to construct a Turing machine generating the same language or accepting the same language. Fine. So I will design M as a 4-step non-deterministic machine. The first step will hold the input. Okay. And the rules of the grammar are embedded in the finite control of this machine M. Okay. The input is always occupy the first step and nothing will be there, nothing else will be there on the first step, and this is never changed. Okay. The second step contains sentential forms in the derivation process initialized by the symbol S. That is, if you look at this example, the second step will contain S and then UT and then AUBCT, AAUBCT and so on, so on, so on, so on. Finally this. Okay. Okay. Fine. The second and the third and fourth steps are used for different purposes for some non-deterministic cases, as we will see. So this machine M will keep on doing this thing. It first non-deterministically chooses a position on the second step, which contains a sentential form. Okay. Just some position with the hope that it can make a substitution of alpha can be beta, alpha, substitution of alpha by beta at that starting from that position. It then non-deterministically choose some rule alpha can be beta, and the knowledge of all these alphas and betas, all these productions are in the finite control of the Turing machine M. So it non-deterministically chooses any such rule, copies alpha to the third step and beta to the fourth step. Okay. Now what the machine will do, as humans do likewise, it will try to compare alpha with whatever position with the substring of the first step. Okay, sorry, second step. Okay, and it will find it has chosen some non-deterministic location. Okay, on the second step, and now first it will validate whether alpha can be found from that position. Okay, so compare step 2 with step 3. Step 2, step 3 the entire content, but step 2 starting from the position chosen for step 2, and how long? It is as big as or as long as alpha is. If it is a complete match, if the comparison succeeds, you replace alpha by beta on step 2. So you derive one step of the you carry out one step of the simulation derivation process. Definitely, if the length of alpha and beta are different, then you may have to relocate whatever follows alpha on step 2. If beta is larger, then you have to move things to right. If beta is smaller than alpha, then shorter than alpha, then you have to move the remaining portion to the left. Good. And after every such step of the derivation process or simulation of the derivation process, the machine compares the content of step 1 and step 2. If they are same, then you have generated a valid string that can be generated by the grammar following this derivation process. Accept and halt. If not, continue. Okay. And one thing that is important about this simulation is that M is not necessarily a total Turing machine. For example, if instead of a cube, b cube, c cube, I give something like a cube, b cube, c4, c power 4, something like that, then no matter what production the Turing machine non-deterministically chooses, it can never generate a cube, b cube, c cube, or something, a cube, b cube, c power 4, a3, b3, c power 4. It can never generate. But it will keep on trying, and this attempt will never fail. Okay. So this is not necessarily a total Turing machine. In fact, unrestricted grammars are equivalent not to recursive languages, but to recursively enumerable languages. Okay. This is an important thing. M is not necessarily total. It may exhibit looping behavior. Good. The reverse construction, the converse construction is a little bit more involved. Now the input is a Turing machine M, and since we have seen several equivalent models of Turing machines. We can choose any particular one that will make the proof as easy as possible. Okay. So this is given, and we want to construct an unrestricted grammar G from M, such that the language of G is exactly the same as the language of M. So how to proceed? So we will, in order to make life simpler, we assume that M is a one-step deterministic machine, and one-step means semi-infinite step, so not open at both the ends. Semi-infinite step, one-step deterministic machine. Moreover, I will assume that M has some particular behavior. If not, I can anyway convert that M to exhibit that behavior. That behavior is something like this. We want M to halt with an empty tape after every accepting. Okay. Not exactly empty. We will see that two markers will continue to stay. Other than that, the entire tape must be empty, filled with empty spaces, blank spaces. If M does not halt, or if M rejects, then we do not make any such assumption that it will have to clean its tape. Okay. It may keep it dirty. Okay. Only after accepting, M has an urge to clean its tape and then halt. So how I can convert some M to this M prime, that this condition is satisfied? It's pretty straightforward. Add a new accept state T prime. So whenever this earlier machine M goes to the old accept state T, okay, when it is the old accept state T, it erases the entire tape and then eventually comes back to the left end marker, then it jumps to T prime. Okay. Only question that we need to solve in this context is that the machine must understand how much of the tape is used. Because as we have seen in many examples, blank spaces are valid tape symbols. And it can store the blank symbol in the working portion of the tape. Okay. So just seeing a blank does not imply beyond that symbol there is no non-blank symbol in the tape. But this problem can also be avoided in a fairly straightforward way. So you must know how much of the tape is actually used. So it will use another end marker called the right end marker. Okay. So that essentially delimits how much of the tape is used. Beyond that, nothing is used. Okay. But definitely, M may want to use more space than whatever is currently used. If so, this end marker is simply shifted right and the new space is used. Okay. So from time to time, maybe M will extend the used portion of the tape by shifting this marker. Okay. And at the state T, before jumping to T prime, it will eventually make these two markers, this and this touch together. Then it will jump to T prime. Okay. It will shift the right end marker to bring it just to this position. Immediately after this, then it will halt. So it's not exactly an empty tape. It is empty otherwise, except that it has a left end marker followed by the right end marker. This is what I meant by the empty tape. Good. So we assume that M has this property. It clears or cleans its tape after accepting. Okay. And then goes to the new accepted T prime. Okay. So my grammar will do the opposite thing. It will simulate the working of M from end to beginning. Why? At the beginning, M gets the input string, whereas G generates a string over terminal symbols at the end. So they have some kind of opposite behavior. G starts starting from capital S, and at the last process, at the last step of its derivation, it generates the final string, whereas M starts with that string and eventually accepts. Okay, fine. So the configurations of M will be my sentential forms for G, the derivation process. Okay. So what is the initial configuration? This is S. Okay. Initially this W is written on the tape of the machine, and you also assume that from the beginning this right end marker is there. If not, you can assume that there is a different start state S prime. The machine will move past W, put that right end marker, once again come back here and go to the earlier start state. So this is not a loss of generality. Okay. So I assume from the beginning that this right end marker is there. If not, we can handle it. Okay. So this is the initial configuration, and because of the final, because of that assumption on the part of M after accepting, its accepting configuration must be of this form. Left end marker followed by its accept state T prime followed by this. So it is pointing to this, and the state is T prime. Okay. Fine. But G will eventually generate a W. Okay. So, okay. Now, these things I must talk about. So, since the configurations of M are the sentential forms, so the non-terminal symbols of G must be whatever is allowed in the tape alphabet, right? I think this is not correct. It is not minus this. It's complete tape alphabet and the set of steps, because we have to have something like this. This is a mistake. It's a complete tape alphabet. Why? This W should be there. Oh, I see. Sorry. The non-terminal symbols. So sigma terminal symbols. The non-terminal symbols are this minus this and Q. And we assume that this Q intersection gamma is empty. Sorry, fine. This is fine. This is a non-terminal symbol. All symbols, sigma is the terminal symbol, set of terminal symbols. The non-terminal symbols are this and Q plus another start symbol S, which is not present in this or this. Okay. Fine. And you recall that, as I mentioned, G will reverse the process of M's acceptance. So this is the final configuration. So this G will start by adding this rule, S can be this. Okay, and it will work backward to find out or to figure out whether it can reach this configuration, which is the initial configuration of M. Once this is settled, okay, this configuration can be reached, and this should go, leaving only W, which is the final string in the terminal symbols alone. Okay, so I add two other rules. S left end marker can be empty and the right end marker can be empty. Okay, fine. So this is how G starts and this is how G ends, leaving behind only W, which is going to be accepted by the machine. The question is how to simulate a step of the Turing machine. So this is what I will now mentioned. So how to simulate a right movement delta p comma a q b right of the Turing machine M. Okay. Now as the Turing machine moves forward from PA to QB and a new H position to the right, the grammar will move in the opposite direction from here to here. Okay. So at this point the simulation is the configuration is something like this. A is the current symbol. This is what this underline says. The head is pointing to this. This is followed by some symbol C. After this movement, A will be replaced by B and the head will move from this position to this position. Okay. Now if I look at the configuration of this machine, this is something followed by P, followed by A, followed by C, and then something. The only local change that is made is something B, new state is Q, then C, something. So you can see PA changes to PA changes to BQ in the configuration, but then since the grammar is simulating the move in the opposite direction, I add the rule BQ can be PA. BQ can be PA. Okay. So the simulation is perfect, right? The simulation of the left movement is slightly trickier. So let's say it's something like this. In state P, read A, go to state Q, after rewriting A by B, and then move left. Now let us look at the situation. Now I have something C, the head is pointing to A, this is replaced by B, and the head is now pointing to C. So earlier the configuration was something C, P, A. Right? Now it becomes Q, C, B. Okay. And the C can be arbitrary. Here the C actually does not come in the picture. It can be C, but it doesn't matter. Here C can be arbitrary, and since it's a left movement, it's obvious that this A cannot be the left end marker. Okay. So, whatever C it is, if I add this rule, QCB or this rule, QCB can be CPA, then the left movement of M is simulated irrespective of whatever C is. Okay. So, that's basically the proof in a nutshell. So M accepts like this: initial state S, W is the input string, left end marker, right end marker. After a number of steps, it will eventually go to T prime with the step blank, and the grammar, unrestricted grammar G, does the same process starting from this. S generates this, eventually it comes here, then this thing vanishes, eventually W remains. Yeah. So that is the outline of the proof, and that settles the equivalence of unrestricted grammars with Turing machines. There is a class of unrestricted grammars that are equivalent to recursive languages, but we will not go through that. I will supply you some notes, or I would say some references. If you want, you can read that thing. Good. Again, like every slide set, there is an exercise set. And yeah, let me stop. So this is all I wanted to cover for today and also for this week. Next week, I will once again come back and we will see what to cover. So maybe we will talk a little bit about undecidable problems, about context-free languages, maybe some other things. And after that, possibly I will start posting solutions of these tutorial exercises. But please try. Don't wait for my solutions. Okay? That will give you some, I would say, practice. Okay, bye. See you in the next week.